In this video, we're going to look at two examples of solving homogeneous type differential equations using the method of substitution. Now, these differential equations are not the same thing we normally think of when we use the term homogeneous, when we can write the right-hand side equal to 0. This homogeneous type differential equation has no relation to that. Confusing, I know. But it's a good day when the name of the problem is the most confusing thing. So let's get into our first example. So what we first need to do is make sure that the differential equation is written in the form of y prime equals some function a of y over x. So we need to make sure everywhere there's a y and an x, it's written in terms of y over x. So we can rewrite the differential equation as y prime equals x squared over 2x squared plus y squared over 2x squared. Now simplifying this further, we just get a half plus a half y over x squared. So now we can say let v equal y over x, and then if that's true, then y equals vx. Now on the left-hand side, we have a y prime and y equals vx. So we're going to write the left-hand side as vx prime. And then the right-hand side of the equation will go to a half plus a half v squared. Now expanding the left-hand side, we just get v prime of x plus vx prime, but x prime is just 1 because it's a derivative of x with respect to x. So we just get v prime x plus v, and this equals a half plus a half v squared. Now simplifying this further, we get v prime of x. So we're just going to move this x over to the other side of the equation, equals a half plus a half v squared minus v. Now we can factor this. So that'll just equal a half v minus 1 squared. Now if we look at this, we can see that it's actually a separable differential equation now. So we can just solve for v. So if we divide by v minus 1 squared, we'll get 1 over v minus 1 squared, v prime, and we'll also divide by x, so that will just give us a half over x. Now this is for x doesn't equal 0 and v doesn't equal 1. Because we can't divide by 0. But we can see that if v equals 1, then in this part here, the derivative of v will go to 0. So we'll actually end up with 0 times x equals a half, and v is 1, so we get 1 minus 1 squared. And this just gives us 0 equals 0, which is the identity. And therefore, v equals 1 is actually a solution. So v equals 1 is a solution. So we'll keep that in mind for the end. Now if we then take the derivative of both sides with respect to x, we will get 1 over v minus 1 squared dv equals a half of 1 over x dx. Now we can solve this. You can either use a u substitution or you don't have to because du equals 1. I'll just use the u substitution and show you anyway. So if we get u equals v minus 1, then du equals 1. So you don't actually have to use a u substitution when du equals 1. You can just sort of take the integral as is. So that will just give us 1 over u squared du, and that will equal a half the integral over 1 over x dx. Now we're just going to get minus 1 over u, and that's going to equal a half times the logarithm of x plus some constant c. Now if we plug in what u equals, we will just get minus 1 over v minus 1, and that will equal a half natural logarithm of x plus c. Now what we want to do is solve for v here. So we can say 1 over v minus 1, and we'll move the negative sign to the other side, a half natural logarithm of x plus c, and then we'll just take the inverse of this, so we'll get v minus 1 equals minus 1 over, that will actually be 2 on top there, so we'll get 2 over natural logarithm of x plus c, then we'll get v equals 1 minus 2 over natural logarithm of x plus c. Now if we remember at the start we let v equal to y over x, so if we just plug this back in, we'll get y over x, and I'm just going to multiply through the x right now. So x minus 2x over logarithm of x plus c, and that's our solution. Now remember that v equals 1 is also a solution, so we'll also say v equals 1. So if v equals 1 for v equals y over x, then this just implies that y must equal x if v is 1. So we have our solution here, and we also have the y equals x case is also a solution. Let's try another example. Here we have a first order ODE. We can see that it's not linear because of the y squared term here, and so we can't use the integrating factor method. It's also not separable because no matter how hard we try, we're not going to be able to put all the x's on one side and all the y's on another side, so we can't solve it that way either. You'll see that for this equation, we'll be able to write it as y prime equals some function a of y over x, and therefore we can solve it via substitution. So let's try and do that now. Let's divide by 3x, so we'll get y prime equals 3y over 3x plus y squared over 3x squared. Now simplifying this a bit more, we get y over x plus 1/3 of y squared over x squared. So if we say let v, that's our substitution variable, let v equal y over x, then we just get y equals vx. And so our y prime on the other side, on the left-hand side, becomes vx prime equals v plus 1/3 v squared. And now if we expand the left-hand side using the product rule, we're just going to get v prime x, and we're going to get plus v x prime, but x prime is just 1, so that's going to simplify again as v prime x plus v equals our right-hand side, v plus 1/3 v squared. So what we can do is minus a v from both sides of the equation, and that will just give us v prime x equals 1/3 v squared. Now you'll see that this is a separable equation, so we can solve it that way. So we can say for v doesn't equal 0, this allows us to then divide by v. We get 1 over v squared v prime equals 1 over 3x. So all I've done here is divide by v squared. Now we can integrate both sides, and that will give us the integral of 1 over v squared v prime dx equals the integral of 1 over 3x dx. And this just gives us minus 1 over v equals 1 over 3, the natural logarithm of the absolute value of x plus c. And now if we solve for v, so we're going to take the inverse and we're going to multiply by -1 to both sides. That will give us v equals minus 1 over 3 natural logarithm of x plus c. And then if we recall that v equals y over x, subbing back in y over x, we get y over x equals minus 1 over 1/3 natural logarithm of x plus c. And then solving for y, we just get y equals minus x over 1 over 3 natural logarithm of x plus some constant c. So that's one of our solutions. You'll see that if we go back up here, where is it? For v doesn't equal 0, we can also split this off and have the case for v equals 0. So if v equals y over x, and if v equals 0, that implies that y has to equal 0 because x can't equal 0. So that for v equals 0, that just implies that y equals 0. And if y equals 0, if we go back up to our ODE up here, if y equals 0, you'll see that we just get 0 equals 0, so you'll get an identity. So y equals 0 is also a solution. And you can also try it just by letting v equals 0 down in this case here, and you'll get the derivative of 0, which is just 0, and then you'll get 0 on the right hand side, so you'll get 0 equals 0 here, and that's just the identity again. So we have two solutions. We have the solution of y equals the minus x case here, and we also have y equals 0, and these are our two solutions. If you liked the video, then please give it a thumbs up. If you found it helpful, then feel free to subscribe. I make regular videos on calculus, linear algebra, statistics, psychology, and physics. As always, thanks for watching.